will remain constant because it is made in terms of time constants, and for all it is time five time constants, five taus. Okay, so but I want to share with you a video. Let me see if I have it ready at the internet. There is a, an example of a problem on how to deal with the inductance charge and discharge uh, processes. Okay, can you see the screen?
Yes.
Okay, I will put it's playing now.
Dielectric online, and here's another application of inductance. In this case, we're going to look at an RL circuit. And an RL circuit is a circuit that has a resistor and an inductor in it. So let's draw an inductor circuit like this. So let's say we have a battery connected to a resistor, connected to an inductor. And the symbol for an inductor is something that looks like that, looks kind of like a coil. And then we're going to add a switch to it. There we go. All right. In our particular example, it says that we have a 50-volt battery that's connected in series with a 0.25 Henry inductor and a 20 ohm resistor, as well as a switch initially in an open position. There we go. Let's plug in the numbers that we have. So the voltage here is equal to 50 volts. The resistance here equal to 20 ohms. The inductance here, L, equal to 2.5 Henries, and the open switch. Now, they're asking for A, how long after the switch is closed will the current reach 99% of its maximum value? B, what will the current be after 0.1 seconds? And C, what will the voltage drop across the inductor be after 0.2 seconds? All right, let's start with part A. We want to know how long it takes for the current to reach 99% of its maximum value. Well, after we close the switch at t equals 0, what an inductor does, it prevents a current change. So if the inductor wasn't there, there was simply a circuit there with a resistor, the moment we close the switch, current will instantly begin to flow through the circuit. But the inductor holds back that initial surge of the current. And so it takes a while for the current to reach its maximum value. Well, there's a time constant associated with this. The time constant, in this case, is equal to L over R. You can see that the bigger the inductor, the longer the time constant is, the more the inductor will hold back the surging current. And of course, the larger the resistance is, the smaller the time constant, because a larger resistor means that the end current will be relatively small, because remember Ohm's law, that current is equal to V over R. So if you have a large R, you'll have a very small final current, and then the time constant won't be as long. So in this particular case, the time constant is L, which is 2.5 henries, divided by resistance, which is 20 ohms, and that is equal to 0.125 seconds, about an eighth of a second. That's the time constant. Just like with capacitors, the time that it takes for the current to reach 99% of its final value, that takes 5 time constants. So for part A, the time equal to 5 time constants is the time that it takes for the current to reach nearly its maximum value. So in this case, this is equal to 5 times 0.125 seconds, and so that would be equal to 0.625 seconds. So that's the easy part. It takes a little bit over half second for the current to reach pretty well its maximum value. The next part is a little bit more difficult. Now we're supposed to find the current after 1 second, or not 1 second, but 0.1 seconds. So for that, we need the equation. So remember that just like with capacitors, when inductors are in a circuit, the current will not immediately go to its final value. If this is the final value of the current, then the current will increase just like that, just like the increase of a charging capacitor. And the equation for that, we can say, for part B, the equation we need is the current as a function of time is equal to the final current in the circuit times 1 minus e to the minus t over tau, where tau, of course, is the time constant of the circuit. The final current of the circuit can be found by using Ohm's law. So we can say that I final is simply equal to the voltage applied to the circuit, which in this case is the volt divided by the resistance of the circuit, which is R. So we can actually replace I final by the voltage in the circuit divided by the resistance in the circuit. So we can write it like that. You can say this is equal to V over R times 1 minus e to the minus t over tau. Okay, so now we want to evaluate that for the time being equal to 0.1 second. 0.1 second is just slightly less than 1 time constant. So I, when t is equal to 0.1 seconds, is equal to the V final over R. So V is 50 volts divided by the resistance of 20 ohms times 1 minus e to t over tau. So t divided by 0.125. And that would be seconds, right? If you want to put the units in, that's seconds. And 1 divided by 0.125 seconds is like 8t, so I can rewrite this as, that would be 2.5 amps times 1 minus e to the minus 8t. All right. Now, plug it into value for t equals 0.1 seconds. We say this is equal to 2.5 amps times 1 minus e to the minus 8 times 0.1 seconds. Let me finish this here with parentheses. Now we grab our calculator. Here we go. And let's plug these values in. So we got 0.8 negative. We raise that to the exponent. And then we subtract that from 1. And then we multiply that times 2.5, but let me plug in what we have so far. That's 2.5 amps times 0.55. And so when we multiply that times 2.5, what do we get? We get 1.38 amps. So that means that the current, when time is equal to 0.1 seconds, is now equal to 1.38 amps. The second part, or now the third part of the problem, so we found our first part of the problem. We found that after 0.625 seconds, pretty well the current is at its maximum strength. Here, after 0.1 seconds, the current is at 1.38 amps. The final current will be 2.5 amps. That happens after 5 time constants. But now for part C, we're supposed to find the voltage drop across the inductor after 0.2 seconds. So for part C, and let me put a line here, so that's my remaining board space, not a lot, but let's see if it works. So C, what we're trying to find is the voltage across the inductor is equal to question mark when t is equal to 0.2 seconds. So there's different ways in which we can do that. The simplest way would be to use, let's say, Kirchhoff's rules and go around the circuit and say the voltage drop or the sum of the voltages around the circuit should add up to 0. So starting at any given point and then first going across the battery, we can say that using Kirchhoff's rules that the voltage across the battery plus the voltage drop across the resistance, that would be a negative, right? Negative voltage drop, that would be minus I times R. And then the voltage drop across the inductor, and the voltage drop across the inductor is L times the change in the current. So minus L times di dt, and that equals to 0. So what we're looking for is we're looking for the voltage drop across the inductor, which is the L di dt. So what we could do is we could simply take the equation of the current, take the derivative of that, and then evaluate that at t equals 0.2 seconds. Or, if we're smart about it, we can solve that equation for the quantity L di dt in terms of the voltage and the voltage drop across the resistor. So let's do that instead. We're going to solve this equation for L di dt by moving to the other side and turning the equation around. So we can say that L di dt, which in essence is the voltage drop across the inductor, that is going to be equal to, on the other side, we have the volt from the battery minus the voltage drop across the resistor. So to find the voltage drop across the resistor, we must know the current at that time, which means we have to solve for the current at 0.2 seconds, which is kind of what we have here when we solve the current for 0.1 seconds. So let's now find the current at 0.2 seconds, which means we're going to take the very same equation here, instead of 0.1, plug in 0.2. So as a quick sidestep, we can say that the current when t is equal to 0.2 seconds is equal to what we had before, which is 2.5 amps, which is the final current when the inductor no longer opposes the change in the current, times 1 minus e to the minus 8 times 0.2 seconds. And that will give us the current that we can plug in here because we want to find out what the voltage drop across the resistor is at that moment in time. All right, plugging that into the calculator, we have, that would be 0.2 times 8, which is minus 1.6, 1.6 minus, use as the exponent of E. So that gives us 2.5 amps times, oh, then we have to subtract that from 1. That's better. So we have 2.5 amps times 0.798. So multiply times 2.5, and that gives us almost exactly 2 amps. Close enough. We'll just round it off to 2 amps. All right, so now we know the current at t equals to 2 seconds, which means we can now find the voltage drop across the inductor at 0.2 seconds. So L di dt when time equals 0.2 seconds is equal to the voltage from the battery, which is 50 volts, minus the voltage drop across the resistor at time equals 0.2 seconds, which is 2 amps times 20 ohms. And then you can see, of course, that is equal to 50 volts minus 40 volts, which means after 0.2 seconds, the voltage drop across the resistor is 40 volts. Subtract that from the 50 volts, you're left with 10 volts across the inductor. So the answer is this is equal to 10 volts. So the L di dt when the time is equal to 0.2 seconds is equal to 10 volts. And that's how you do that. Well, and then we're
Okay, so you have seen how use different tools. He even uses the Kirchhoff's law to obtain the voltage of the inductor, just knowing that the sum of all voltages around a circuit must be equal to 0. But we will see that in the unit number 2. We will see Kirchhoff's law. But for now, I'd like to share also with you uh, also about this. Let me show you first the presentation here. Uh, I mean, when I say the presentation, I mean the Power PowerPoint presentation. And here, okay. In this case, want to first look at this problem. This is, we will go back to our capacitance studies because it behaves very much the same as the inductors. Here also we have time constant. Here the time constant tau equals RC. So in this case, we are going to analyze what happens to the circuit two moments. First, in the moment of charging the capacitor. You know the capacitor will be charged when connected to a battery until it reaches its final value, that is the value of the battery. Here we have E equals 12 volts, and so the capacitor will be charging until it reaches the 12 volts level. Okay, but how it does? Okay, first we have here a switch. In the first moment, we will have it open. I mean, in the moment zero, we will have it the switch open, so there is no connection at all. There is no voltage. But immediately at the moment of closing the switch, it will start running the time. But for the moment exact of closing the, we will have uh, the voltage of the resistors will be immediate, but the voltage in the capacitor will be 0 volts because we are in this very point in uh, the zero time. Then it will continue to grow. While here also we don't have current, but we will have a change in current from the initial value to another to any value that we are not going to calculate. We are not calculating the current here. We only are going to calculate the voltage. And for the voltage, we are going to use this equation. Yes, for this time will be, well, let's define the time constant. The time constant is, as I told you, is RC. And we can put in the time scale as 1 tau, 2 taus, 3 taus, 4 taus, 5 taus. 5 time constants. You know, we will have the value of the time constant depending on the value of the resistance and on the capacitor. In this case, we are not calculating because we don't have the values of R nor C. But we are going to put it into this equation. The equation for the voltage here is the voltage in the capacitor. We should have put here VC is equal to the product of E, which is the voltage, times this expression, that is 1 minus this exponential expression, that is the number E. E equals approximately 2.72, but this is the base of the Neperian logarithms. So You don't have to complicate, you just have to learn how to obtain the value from your calculator or from your cellular. This expression is e to the minus to the power of e minus t, the variable t that is growing, this variable, divided by a constant that is rc, is the tau, t divided by tau. So if we have this scale in taus, we can put here or substitute for the several values of tau, tau, 2 taus, 3 taus, 4 taus, and 5 taus. And dividing this by tau will give us -1, because here is a minus sign, -1, -2, -3, -4, -5. And then we can do the calculation. For example, here is a table that shows first the percentage of growing. If we cut plot here to the 100%, we will say that at different moments, these are different moments, we'll have 63%, 86%, 95, 98, or 99% from here. Here we have to the 99%, yeah, 5 tau, almost 100%. So for the expression, we will have to calculate. You know how to do it with your calculator? You can do it in the computer. Are you watching this? Ah, no, okay. I put in the calculator. First, let's calculate e to the -1. What do? We take our calculator, push the number 1, then push the plus minus symbol, that is change sign. Now we have -1 in the screen. Then we go to the function of the scientific calculator and find the key e to the x. So -1 is the x in this moment. So e to the x would be e to the -1, and will give me the value 0.3678. No? Okay. This value is this one. But we have to subtract it from 1. What I do is I put this -1, but it will give me a negative number, and I change the sign, and it gives me 0.632, which is this. We multiply by 100, and we have the percentage here. And so it is -1, -2, -3, -4, and -5. And then to obtain the voltage here, we multiply. We already have evaluated this part of the expression. We have to multiply by E, which is 7 volts, then times 12, and it makes 7.58 volts. Okay? Now let's make it for tau equal 3. It has to give us 95. We put clear, and we put the number 3, change sign, e to the -3 -1 equals, and change sign. It gives us 95%. And so it gives us 0.95. And then we have to multiply this times the voltage, which is 12 volts, times 12 equal 11.40. Okay, 11.4 is correct here. And then let's calculate for tau number equals to the time equals 5 taus. Then we will be 5 tau divided by tau will be 5, and this minus 5. So again, I put 5, change sign, e to the minus 5. It gives us 0.0067. This 0. Is in decimal form. If you want in the percentage value like here, okay, excuse me, it has still to be subtracted from 1 minus 1. And change sign, it will give us 99.3. It will give us 0.993. We multiply by 100, we have the percentage. What we have before we multiply for 100, we multiply 0.993 times 12 volts equals 11.92 volts. So in this time, it grows from 0 to 11.92. It is very close to 12 volts. It will not, in the formula, it will not reach exactly the 12 volts because it is a, a, a hyper, ¿cómo se llama? Bueno, ¿cómo se llama? Es como una hipérbola, hyperbolic curve that will never touch the, if it can go to infinite and never touch the 12 volts value, but every time will be closer and closer and closer. So for practical matters, we can leave it that for 5 taus, we will have almost the 100% of charge. Okay. Now for the discharge process, we have this another formula. I put it here outside the paper. I put BC, that is the voltage at the capacitors. Okay, sorry. Then we finish this. It's completely charged. We can open the circuit here, and the capacitor will remain charged. But now let's make another thing. Let's remove the battery, and we will have a circuit like this. We'll have the switch, the capacitor, and the resistor. I put it in a different order, but that doesn't matter. Thing is that when we close this switch, the capacitor, which now is charged at 12 volts, will start to be discharging through the resistor, and will be doing this according to this expression. Voltage in the capacitor will be voltage 0, which is this one, the initial voltage, let's say. I could put the letter E, but because we removed from here, I just put V0, the initial voltage. This we multiply it by the exponential expression, only e to the minus t of time divided by tau. And again, we can go from 1 tau, 2 tau, 3 tau. For 1 tau, it would be e to the minus 1, then multiply by this. So I start with minus 1. I put the 1, I change the sign, I put the e to the 1, and it will give me my point 36. I am here now. I didn't put appropriate title key, but it starts, the second table starts here. For tau 1, it will be 36.8%. Then I will multiply this by the initial value, which is 12 volts, equals 4.41, and I put here 4.42 volts. For number 3, let's say it must be 5%. Let's check. I put number 3, change sign, then e to the minus, it says 0.497. I rounded here to 0.05. Multiply by 100, I will give me 5%. But if I multiply the 0.05 times the voltage, it will give me very close to 0.6. Actually, give me 0.597. But for practical purposes, I put 0.6, and it in the value of 5 taus. I'm checking also just I'm making as an example, just that you know how to make the calculation. Put the number 5. I hope you are following with your calculator in your hand. You put 5, change your sign, then go to the e to the x, and gives you 0.0067. And then we multiply this times 12, and it gives 0.08 volts, which is not 0 volts, but is very close to 0 volts. It's 80 millivolts. Okay? Well, that's for the capacitor. For the inductor, I have set up this circuit, which I want you to make me as a project for next Monday and add to your qualification. I want you to do a simulation of this in Multisim or in LiveWire, so that you can put here an current meter, an ammeter here, and that you will record how this curve will be growing. Okay? So that will be the object of the simulation. Okay, it's very simple. You can use these values, or you can choose other values. But let's see how I did make the simulation in Excel, because I am having some problems now with LiveWire and I mean I cannot connect the oscilloscope here. I want to connect an oscilloscope here to measure the current and show the graph how it's coming, but I cannot make it. I had done it before, but now I think I need some kind of proof or probe, una probeta. They use probes to measure the current even in the software, but I don't I have not remembered how to do it in Livewire. And in the multisim, I know how to do it, but I have problem with my license. I'm working on it. But in the meantime, I made this, which we can see, and I will share with you also this. This is not only an image. Here it seems it is an image, but if you do it double click, you will see that it's actually Excel. You can change to, for example, 50 volts. Then the current will be different, 2.5 amperes. We have how it was, 20 volts? No, I forgot. They give you 1 amp is the maximum. Okay, so you can change with this. This is an actual file. I have here implemented the the table for the several values of tau. I put this intermediate result is just the exponent value. Actually, perhaps it is not necessary, but for didactical purposes, I put it here. And okay, I will stop sharing, and I will show you also. Also, I will show you another. I don't have. This is another simulator, Excel simulator for the capacitor. Here we can show charge of the capacitor and discharge of the capacitor. Here I have put the value of R and C, and I put them in the formula and have obtained here the value of the time constant tau, and then I made also the same. I put here tau divided T divided by RC. I didn't put here the letter tau, but I could. But you can put here more directly the value of R times, then you can multiply, and you will have the value here, 1.34. I put here two different values, but aquí da 2.68, aquí da B6 por 5, ¿dónde está B6? Ah, aquí esto es 5 taus, porque aquí es un tau, y aquí es también un tau, ¿ok? Un tau, 5 taus. Entonces, pero aquí no podemos el valor, nomás ponemos, acuérdense que tengo desfasado eso porque no supe cómo hacerlo bien. Aquí debería ser el 1, el 2, el 3 y aquí el 0. Entonces aquí tenemos 5 taus, podemos ver aquí el valor, dice que es 11.919. No alcanza a ser los 12 volts, pero casi. Y aquí para la bajada, pues sí es de 12 volts, es en la descarga, y alcanza a llegar aquí a casi cero, da 0.08 volts, que es este valor de aquí. BC y BC, en caso de carga y en caso de descarga. Entonces, les voy a subir estos dos simuladores. Bueno, yo les llamo simuladores, simplemente son hojas electrónicas, tal vez de haberlas puesto en un solo archivo, pero para que si les sirve la puedan usar para hacer cálculos y me voy a dejar de compartir. ¿Ok? Entonces, como me doy otra repasadita a la lista ya para cerrar la clase. Ir desde la resistencia, un poco de ley de Ohm, calcular si les doy el voltaje y la corriente, pues calcular la resistencia o viceversa, ¿no? Poder resolver cualquier problema de esos, calcular la potencia. Acuérdense de las fórmulas de la potencia, que la potencia es igual a I cuadrada por R o a B cuadrada sobre R o a I por B, o sea, corriente por voltaje. Después, también cálculo de la resistencia en función de la resistividad. Normalmente va a ser del cobre, para que tomen nota ahí del valor de la resistividad del cobre y la puedan aplicar. Y de las variaciones respecto a la temperatura, que si va a ser escrito, sí, yo les voy a mandar el examen y ustedes en una hoja en blanco, el valor en blanco, digo, es que me confundí. En una hoja en blanco ustedes, digo, si imprimen la hoja que les voy a mandar, y ahí llenan sus datos, y ahí mismo lo contestan, la fotografían y me la mandan, me la suben como tarea, la voy a poner el examen, lo voy a poner en Classroom, y de ahí me lo suben como si fuera una tarea, y yo lo voy a calificar, ¿sí? Para que todo esté ordenado en el ambiente de Classroom. Y el valor de cobre, está en una de las presentaciones primeras de PowerPoint. Viene una tablita y ahí viene como un pegoste de una fotografía que saqué de una tabla y ahí viene la resistividad del cobre. Eso si no les doy el valor yo ahí mismo, ¿no? O si tienen duda me lo preguntan ahí mismo. Yo creo que el examen lo vamos a hacer en media hora, ¿sí? Porque voy a hacerlo, en vez de que hagan 10 problemas, nos voy a poner a que hagan 2 problemas, van a ser, vienen como 20 problemas y de acuerdo a su número de control, si tienen su número de control termina en 0, van a ser solamente el problema 10 y el problema 20, ¿sí? Porque terminan en 0. Si termina el 1, pues van a ser el 1 y el 11. Si termina en 2, pues el 2 y el 12. Y así van a ser 2 problemas. Y voy a ver la manera de ponerles otro problema de rescate. ¿Sí? Pero el chiste es que no se vayan a tardar mucho en hacerlo y que tampoco sean muchos problemas. ¿Ok? Bueno, ándale, pues entonces ahorita, pues ya me voy a retirar. Les deseo que les vaya bien en el examen. Nos vemos mañana.